Okay, we're back from our break, and we have a little bit more left with this adsorption. Let's talk about some practical things that are going to happen when we have adsorption and how it's going to affect your electrochemistry. One of the really annoying things that happens with normal electrochemical experiments is you get adsorption of electro-inactive species, technically known as crud. And this can be a problem because a lot of times the electrode response is completely distorted by these inactive species. They adsorb at the electrode surface, and what usually happens is that, especially with solid electrodes, you have sites on the electrode that are more active for electrochemistry than others, and that's where these they have a higher surface energy, and that's where these things tend to adsorb at, and so that tends to greatly remove the activity. And this adsorption is a problem also because even small amounts of material in the solution will cause significant adsorption on the electrode surface. You can calculate for yourself, but you read very, very tiny amounts of adsorbable materials in your solution, and if you have a significant volume of that, that can easily be adsorbed onto your electrode within a very short period of time, and you'll get a significant decay in your response. And almost anybody that's done any electrochemistry will attest to that, that these surfaces can be very sensitive to the absorption of other species. Now, generally, you can kind of try to model this blocking effect of the adsorbed species. And one way that people have done it is to define a coverage factor. Again, our favorite Greek letter theta is used. And theta would just be the fraction that would be covered by your adsorbates. And so you could say, well, my K0, the rate constant at that adsorbed electrode, is going to be different than what would be otherwise. So you could say K0 net is just going to be K0 for the amount of theta that would be equal to 0, subtracting off that amount. So in other words, the K0 if nothing was adsorbed, and then taking away that fraction of the surface as a multiplier, and then plus the K0 of the covered species times the amount of covered surface. In other words, the fraction that's not covered would be the would have the normal K0. The fraction that's covered would have the K0 that would occur at the covered material. So even though something's adsorbed, you can still get electron transfer through that adsorbed layer. Typically, that K0 is going to be smaller for an active species. But not always. Sometimes that adsorbed material may have, in fact, a more rapid electron transfer rate. In this case, you'd get a catalytic effect. So if we have a blocking layer of adsorbates, K sub 0 sub C would be 0 or very close to it. You can get a catalytic layer. K0C would be greater than K0 theta equals 0. And sometimes blocking K layers are actually useful, and people purposely design their experiment that they get a blocking layer of adsorbates. For example, often people are interested in decreasing rates of reaction. It seems unlikely, but in fact people do, especially for plating applications. It turns out for good plating of metals, you often want the material to go down in a very smooth, uniform way, and that does not happen if you have a very active surface. Let's just give you an example. Suppose we want to plate a part that's got a very narrow channel here. And if you want to plate that with a uniform layer of some metal or polymer, you want it all in here. But if the rate is very rapid at here, what's going to happen is that you're going to get a very thick layer of this built up on the outer part of that material and a very thin layer in that channel, or maybe none at all. But if you make the rate very low overall, then there's enough time for material to diffuse into that thin channel, do the plating, and then go back out. So your overall process may take longer, but you'll get a more uniform result, coating as a result. Also, metal surfaces, especially when they're plating, can have active sites that plate very much more rapidly, and so you'll get blisters or bubbles of or an additional amount of material plated there. And then adsorbates are used to even out the reaction across the surface. Also, inhibitors or blocking adsorbers are used as corrosion inhibitors. The active sites where reactions tend to occur is also going to be where corrosion occurs. So if you put in a material that adsorbs at those active sites, they will tend to inhibit corrosion at the sites because they're no longer available for the corrosion process. Typically, though, in a normal electrochemical experiment, you're not interested in decreasing the rate or decreasing the corrosion, so you tend to not be interested in blocking layers. Catalytic coatings are nice because they can reduce the amounts of expensive material that is required to do a reaction. For example, if you can coat a surface with a small amount of a catalytic adsorbate, you can do a reaction much faster than you could if you had a complete, or much less expensive than if you had a surface that was completely covered with this catalytic material. And the reason isn't always so clear, but let me see if I can explain it to you. Suppose we have an electrode that had some catalytic particles on the surface and an electrode that has a complete coverage of this catalytic surface. What's the difference going to be of the two? Well, if we have a complete coverage of this material, you're going to get planar diffusion to the surface, and you'll get a reaction that's going to be limited by this planar diffusion process. If we have small particles, remember, we get kind of spherical. They act like little microelectrodes, and they'll get increased amounts of mass transport for those catalytic particles, and in fact, at some point, you get an overlap of these diffusion fields for these materials, and you tend to get a diffusion field that now is similar to linear diffusion as you're significantly away from the surface. So what you're saying is that you're going to get the same net amount of material diffusing in as you would if you had a complete surface covered with the catalytic material. But because you're using much, much less of it, you're going to get an increase in the efficiency or the economy of the material. So you might put very small amounts of noble metal particles on a carbon electrode and get an increased activity for the reaction in that way. And that's, and then if you look, an interesting result is if you look at the current time result for an electrode like this. For example, suppose you have a small set of disks on a larger planar electrode, each of these acting like little microelectrodes. Well, you'd get two behaviors under two limiting cases. For large electrodes, you'd get a behavior something like this. And for a small electrode, you get a behavior something like this. And the difference comes because as a large electrode, you get a planar type diffusion. As a small electrode, you'd get this convergent or radial type diffusion process. In between those 2 points, what happens? Well, when the time is very short, you're seeing only the point where you're getting this convergent type diffusion or radial type diffusion. So the array of electrodes act as if they're all independent of one another. And so you'll get a current that will be a sum of all of the things, but they'll act as if they're each one. So if you normalize the current by the the number of electrodes, you'll get a curve that looks something like this that will follow along the same curve as if you had a small electrode. And then at long times, though, you'll get current that looks as if the whole electrode is covered with this material, and you'll get this behavior in the middle. But in the meantime, in the middle, you'll get a shift over like this. So at some point, just as these things start to overlap, you'll see a change in the behavior from the effect of what looks like small electrodes to what looks like larger electrodes, and you'll get this convergent behavior. So one thing, in fact, people have used this, they've used this idea, they've taken small, not only for small catalytic electrodes on a larger electrode, but they've used small arrays of microelectrodes to maximize the amount of current they get while minimizing the amount of expensive material they're using. For example, if you want to use gold electrodes for detectors and chromatography, but gold electrodes are a little bit expensive, especially if they're fairly large. So the idea is that if they use gold particles in a polymer matrix, each little gold particle is very small, and so you can use much less gold as if you would if you're using a solid gold electrode. But you can still maintain the activity as if it was an entire large electrode by operating in this region here, where you've got a large electrode behavior. So that makes some economy there. Now, one disadvantage of this is that the rate of electron transfer would appear a little bit slower on these electrodes, because if you think about this as being one big electrode, the entire so-called apparent area of this type of electrode would be the entire size of the electrode, but the true geometric area is much smaller. And you really remember the current density is what sets the rate constant. And so when you have a smaller number of disks, the current density at each disk is going to be higher than what is apparent, because you've got the difference is the relationship between the apparent and geometric areas. And so CVs in none of these cases look irreversible. This type of behavior has been implicated in lots of electrochemistry, where you take an electrode and you do an electrochemistry experiment on it, and the reaction appears slow, even though you know it should be faster. And the idea is that the metal electrode or carbon electrode has active regions on the surface that act like arrays of microelectrodes, or small little electrodes. And so the reaction is only really occurring at these very tiny areas on the surface. But because you're using this big, large electrode that's mostly inactive, the rate appears smaller than it would normally appear. And so the catalytic effect is somewhat similar. So you can think of catalytic sites as saying sites in an insulating matrix, or sites that are much faster in a conducting matrix would be a similar type of behavior.